Hello and good morning. Please, can you hear me?
Can you say?
Okay, thank you. Welcome. Um, I hope you're all doing well. 4th of July. Today we want to try and finish up with Unit 1. Um, so if you remember in Unit 1, we were supposed to look at limits and functions, logarithm functions, parametric functions, and then differentiation of inverse trig functions, implicit trig functions, and then some engineering aspects. So today, the material we have, lecture 3, we are going to take care of the inverse trig functions, implicit functions, and some applications. Hopefully, so that from next week, we'll start looking at Unit 2, various applications to the derivatives. Okay, so on your screen, that is what I have for you. We want to look at the inverse trig functions, how to differentiate them when you are given functions and you are supposed to differentiate using implicit approach, and then some applications. At the same time, on the LMS, I have placed all the materials with respect to what I'm about to do. So the current PowerPoint, lecture 3 PowerPoint is here. And then the various worksheets to go with today's work is also here. Okay, so you have all the materials which I'm going to use. Okay, so let's go straight into the PowerPoint, using the PowerPoint to explain what inverse trig functions are. Okay, so I'm going to take them one by one, and then we'll try and do as many examples as possible so that we won't leave here um, being familiar and conversant with the method. Okay, so like I said, we are looking at three things: um, inverse trig functions, then we'll look at implicit differentiation, and then we'll look at some applications, both in engineering and non-engineering aspect. Okay, so how do we go about this? First of all, we want to derive the various formulas that are involved in inverse trig functions. How do you derive them? It's actually making, if you are differentiating with respect to x, if you differentiate y and give you x, if you find the inverse of it, then you make x a subject. So it's like if y depends on x, then if you make x a subject, then you are finding the inverse of a function. So we are going to derive these formulas. When we are able to do one, I'm sure the rest, they become easy. Then how do we apply the formulas to solve the various inverse trig functions? Okay, so some problems involving derivatives as well will be involved in this. So let's see how to derive these formulas. Now, inverse trig functions, they come under a type of functions that we call transcendentals. Now, transcendentals functions, they are functions that are in the family like the log and exponential functions. They actually are, you have to follow the formulas to be able to derive them. So log functions is one, exponential functions is one, trig and trig inverse functions are also one. And then when you are giving hyperbolic and inverse functions, so we just categorizing the type of functions we are going to deal with this morning. So we've done log already. We've done look at exponents already. Last semester, we look at trig functions. But today we are looking at the inverse trig functions and how to be able to differentiate them. So that is the type of functions we are dealing with. Okay, so now we want to learn how to derive the formula. When we're able to derive the formula, the rest We just have to put the formulas in a question. You don't need to derive them anymore because they now become standard functions. Okay, so when you are given, let's say, a function y in terms of x. So if y is a function of x determined by the relationship, we were starting with a very obvious one. Let's say sine y is equal to x. If sine y is equal to x, then y is called the inverse sine function of x. In other words, if sine y is equal to x, if I make y the subject, then y becomes sine inverse. I hope you see if sine y is equal to x, then if I make y the subject, it becomes sine inverse of x. So this is where we are starting from. So if sine cos y is equal to x, then y will be called cos inverse. If tan y is equal to x, then y will be called the tan inverse. So we are starting from this route. Define a trig function in terms of y. Then if you make y the subject, then you might find the inverse of that trig function. Okay, so this also means that y is the angle whose sine is x. I mean, that is another way of reading this as well. So in general, if we are dealing with in all the trig function, sine y is equal to x, then it becomes sine inverse. Cos y is equal to x, it means cos inverse. Tan y is equal to x, then the y will be equal to the tan inverse, on and on and on and on. So all the trig functions, this is how we find their inverse equations, or this is how their inverse equations are defined. Now, also remember that in trig, we are dealing with angles. So you must know the value of y, where it ranges from. For sine function, sine is from minus pi over 2 to pi on 2, cos is 0 to pi, and tan is from minus pi on 2 to pi on 2, cot is from 0 to pi, and then sec is from 0 to pi on 2, cosecant and all that. So all these angles we should be familiar with. Sometimes we need to interpret the results we are getting. So you must go back and look at which ranges of the trig, the Cartesian plane, and where that angle is falling to be able to explain them. Okay, so all these things are definitions, so I hope you can follow them. Okay, so this slide, I was trying to break it into simple parts, but I realized if I put into another page, we may not follow. So I've placed everything here. So let's take our time and see how the derivation goes by. Because we are recording, if we need to go over, maybe when you watch the video, you'll be able to follow. But like I said, when you're able to know how the formulas are derived, when you're given a question, you don't need to go through all this thing I'm about to show you. Okay? We are starting from here, and we must make sure that anytime they give you sine inverse, you quote this. And why do we quote this? Is the steps are involved here. So let's take our time and go through the steps. So in finding the derivative of sine inverse of this, we use the definition of the inverse function, which we have seen a few minutes ago, that if you are given sine y is equal to x, where the y lies between minus pi on 2 and pi on 2, then what do? Differentiate with respect to y. So we have to differentiate the left-hand side of this and differentiate the right-hand side of this. So look at this. If I differentiate sine, what do I get? If I differentiate sine, I'm going to get cos. I hope you know that. Okay? So the left-hand side, if I differentiate sine y, it will give me cos y. Now, remember, I'm differentiating with respect to y. Now, this function here is a function of x. So it becomes dx over dy. Okay? So sine y differentiated becomes cos y. And then the right-hand side becomes dx dy. Now, it is actually dy dx I want. So if I invert this right-hand side of the differentiation, I'm going to get dy dx is equal to the inverse of 1 over cos y. This is where the whole thing is. Okay? Yeah, I'm seeing Kingsley here. So please, I hope you are following. Differentiate the function of y, and it gives me cos y. And then the right-hand side gives me dx dy. Now, I want to find dy dx, so I invert this equation and gives me that. Now, then last semester, you remember that we learned that when you square cos and you square sine, it gives you 1. I hope you remember that function. I should have quoted it somewhere here. We call it the identity equation. That is, the cos squared of a function plus the sine squared of a function will give you 1. So if this cos y is equal to, if I want to make cos the subject, then it will be 1 minus the sine squared of the subject, because remember, sine squared plus cos squared will give you 1. So if I want cos squared, I want cos of the function, I must find the square root of 1 minus sine squared over y. Now, but what do we know about our sine squared? Our sine squared here, sine squared y, remember that sine y, remember this one, this is sine y. Sine y is equal to x. So if I say 1 minus sine squared, it becomes 1 minus x squared. I hope up to this stage you are following. Cos y will be 1 minus sine squared y. But I know that sine y, from the beginning, we define it at x. So it means that 1 minus sine squared becomes 1 minus x. So therefore, this 1 over cos y simply becomes 1 over 1 root of 1 minus x squared. So that is the formula. Now, then we go back and look at the dy dx. So dy dx gives you 1 over square root of 1 minus x squared. But we already know that when you want to make y the subject, it gives you sine inverse of this. So sine inverse of that means that if I differentiate this function that I have here with respect to x, differential of sine inverse of x, it will simply give me 1 over square root of 1 minus x squared. Okay, so that is how we are able to come with the standard differentiation, that therefore, anytime we are differentiating with respect to the trig function, the inverse trig function, it is always 1 divided by 1 minus the angle squared. The angle is, if it's sine x, it becomes sine, if it's sine y, it becomes y squared. If it is sine x, it becomes x squared. If it's u, it becomes u squared. So therefore, 1 differential of sine inverse of u will always be equal to 1 divided by square root of 1 minus u squared. Then you differentiate the angle itself that you are given. Okay, so this page gives you the step-by-step approach of how we are able to get these formulas that we have on the right. Okay, anytime you are given a trig function, we only have to quote these formulas on the right, and then we define it. So we can derive the rest of the formulas following the same route. You define y in terms of sine in terms of y, cos in terms of y, tan in terms of y, and go through all these routes. So I have given a summary of all of them, so you don't need to go through. If you want to take your time and verify what I've done here, you can. But so if I'm finding sine inverse of, let's say, u, we will know that it becomes 1 over square root of 1 minus u squared du dx. If I want to find cos inverse of u, then it becomes negative 1 over square root of 1 minus u squared. You negate that right-hand side, then you differentiate the angle. If it is tan, it becomes 1 over 1 minus u squared. If it is cot, it becomes negative 1 over 1 plus u squared. If it's sec, then you have 1 over u, then square root of u squared minus 1. And if it is cosecant, it becomes negative 1 over u square root of u squared minus 1. So sometimes in certain textbooks and certain questions, when you are given the problem, they may give you a hint of what is the standard differentials of the trig function, so that you just will pick the differential equation and then their standard operators and then use them. Okay, so what we are going to do in the next few minutes is to take examples of trig functions involving sine inverse, cos inverse, tan inverse, as many as we can. Okay, if you're able to do that, sorry about that. What's all this? Oh. If you're able to do that, then I'm sure when you see a question or you go through the worksheet, you'll be able to handle it. So let's start with a very simple one. Please remember, we are dealing with inverse trig functions. So here, if you're comparing the formula here, my u here, the u function here is supposed to be, in the question, is supposed to be x to the power 3. So we want to differentiate sine inverse of x to the power 3. Okay, so let's go through it step by step. I've done this one, the rest we'll do it together. So I'm quoting the formula here that sine inverse of u becomes 1, the inverse of 1 over square root of 1 minus u squared. Then you differentiate the angle itself. So my first differential will be, I'm quoting the formula, 1 in the numerator, the denominator becomes 1 minus, u is x cubed. U is x cubed, so it becomes 1 minus x cubed all squared. Now, when I differentiate x cubed, I'm going to get 3x squared. Okay, so now the numerator now becomes 3x squared divided by 1 minus x to the power 6, because x cubed all squared will give you x6. Now, please, if you follow the question says that first of all, find a derivative and then simplify. Okay? Sometimes when we solve problem, we don't want to get square roots in the denominator. So you don't stop here. We want to get rid of the square root sign in the denominator. What do we do by that? We multiply and divide by exactly the square root sign here. So I decided to multiply the numerator with the square root of 1 minus x cubed, x6, divided by the same function. And then finally, you realize that my equation now reduces to 3x squared. Then the square root now moves to the numerator, and the denominator becomes a function without the square root sign. So when it says simplify, and you are here, you've gotten to this stage, then you multiply through and divide through by the function under the root signs to get rid of the square root sign in the denominator. Okay, so any questions? I hope this is straightforward. We identify the trig function. This is sine inverse. You identify your u, which is x cubed. Then you use the formula 1 over 1 minus u squared, then du dx. Okay, so let's do another one. This time, let's do it together. I don't think this one I've done it, so let's do it together. Here, we are supposed to go through the same derivative of the function, and we are supposed to simplify our results. This time, we are using the cos inverse, the trig function in cos inverse. My angle is 3x. So remember the formula. The formula is negative 1 over 1 minus u squared. Okay, so let's work this one together. Okay, so the numerator is 1. My negative is here. Then 1 minus u squared. That will give me 1 minus, my u is 3x. So that gives me 3x like this, all squared. Okay, that is 1 minus u squared. Then I differentiate 3x. Now, if I differentiate 3x, I hope you remember that it will give me 3, because the power here is 1. 3 times 1 will give you 3. Then 1 minus 1 will give you 0. So how far can we go with this? Now, so my numerator is now 3 in the numerator. And then my denominator will become 1 minus 3x all squared should give me 9x raised to the power 2. Okay. Now remember, we are supposed to simplify. So this is what I have now. Okay. This is what I have now. So it means that I must take this denominator and multiply the numerator and the denominator by what I have. So whatever I have here, the numerator here is 3. The denominator down here is 1 minus 9x squared. Now, then I have to do the same thing by multiplying the numerator and the denominator by the root of 1 minus 9x squared. So 1 minus 9x squared in the numerator will happen. Okay, save time. Let me just copy and paste here. Okay, now, so what happened to the numerator? The numerator will simply become 3 multiplying the root sign. So here, in front of this, I'm going to get minus 3, and then the denominator is going to be what I have here. This time, the denominator will no more have the root sign. I'm only going to have 1 minus 9x squared. And that should be the differential of cos inverse of 3x. Okay, so if we follow the formulas, we should be able to differentiate the function one by one. Okay, any questions? Hope you are okay. Okay, so let's try another example. This time we are looking at sec inverse of 2x squared. Sec inverse of 2x squared. Okay, so the same thing. We will define the function. The formula is 1 divided by the function itself. Then this time is u squared minus 1, not 1 minus u squared. It's u squared minus 1. So let's put our function u is 2x squared. So let's substitute that into this formula. We are going to get, so here, the numerator is 1. The denominator will give you outside the root sign, we are going to get u, which is 2x squared. And then under the root sign, we are going to have u squared. U squared obviously is going to give me 4. Okay, well, let me write for the first time. So 2x raised to the power 2 all this squared then minus 1. Okay, and then when you differentiate the function itself, we are going to get 4x. 4, x minus 2 minus 1 will give you 1. Okay, so that is the denominator. So how do we simplify it? When you simplify it, the numerator becomes 4x, and then the denominator, we're going to get 2x squared. And then down here, we're going to get 4x to the power 4. All this minus 1. Okay. So now we have this. And remember, we have to simplify. If we simplify, look at this 4 in the numerator here. And then this 2 in the denominator there. And then you have x in the numerator here, the x, and then the denominator here, we have x squared. So x will cancel one of the denominator x. But the term under the square root sign, this one, we can't do anything about it. So we have to multiply the numerator and denominator by the term under the square root sign. I want to copy so that I don't go through all this write-up. Okay, so when I come here, 2 will cancel 4, and I'm going to get 2. And then this x will cancel x squared, and I'll be left with x outside the brackets here. Now, the denominator will simply become 4x to the power 4 minus 4. So I'll multiply the numerator by 8 and divide the denominator also by 8. Multiply and divide. Now, that will reduce my numerator to become 2. Then the square root sign will become 4x to the power 4 minus 1. And then the denominator will be left with x into brackets 4x minus 1. You can either expand this or you can leave it like that. Okay. Any questions so far? I'm going gradual so that I don't lose out on anyone.
Hello, sir.
Yes, please.
I just wanted to know whether is there instances where they will ask you to prove the formula.
Okay, but it may depend on what you are supposed to do, what question you are supposed to solve. But basically, because the formulas are standards, sometimes they even provide you with a formula so that you don't go through that route. Okay,
Okay.
so basically we may not necessarily ask you to prove the formulas, but what I would advise is that maybe take an hour or so and understand how the steps are like, so that in case you may have to prove it, you know what to do. It's
Okay.
simply differentiation from one side to the other. So then you substitute using the identity, and then in the equation,
Okay.
the standards comes in. But basically, questions you'll be asked to either differentiate with respect to a trig function and then maybe explain your results. I mean, when we get to the
Okay.
application, you'll see how to handle it.
All right. Thanks.
Okay, you're welcome. So thank you, Raymond. We'll take one more, basically, and then I'll try and see maybe one or two more. Then we'll go and look at the implicit one. Okay. So find the derivative of the function and simplify the result. So this time we are finding the cos inverse of this. Now, for the sake of what we're about to do, I wanted to write the square root of x as x raised to the power 1 over 2, so that you can, when we are using the formulas, you can see what we are doing. Okay, so, and then this is 2 cos that. 2 is a constant, so all we need to do is to concentrate on the cos inverse. So let's look at, okay, this one I did it. Okay, so here we are using cos inverse is 1 over negative 1 over 1 minus u squared. So this is the 2, which is a constant, and then my numerator becomes the negative 1. Then 1 minus x squared becomes 1 minus x to the power half, all squared. Okay, then when we differentiate this function, you know x raised to the power half. When you differentiate this, half will come and multiply, then you subtract 1 from half. So it becomes x to the power negative half. The negative will make this to become a reciprocal. I hope you remember. When you differentiate x to the power half, it becomes half times x raised to the power negative half. And the negative half becomes the reciprocal. So 1 over 2, then the x to the power half goes to the denominator. Okay, so that will be the first part. Then we now will take our time and simplify. This 2 coefficient of 2 here will multiply the 2 here, and they will go away. You'll be left with the numerator as negative 1. And then we simplify what is the denominator. The denominator, that gives you half here times 2 will give me x. So the 1 in the under the root sign becomes 1 minus x. Then this term you have here, all this times root x. Okay, all this times root x, because that is x to the power half. So that gives you root x. And then when you put them all under the square root sign, it gives you x into bracket. Sorry, square root of x into bracket 1 minus x. Now we want to simplify this. You know the technique. You multiply the numerator by what is under the root sign and divide it. So when we are done, our final answer should look like this. Negative into bracket, and negative square root of x, 1 minus x, all divided by x, divided by 1 minus x. So the rest of the trig functions, you just will have to either derive the formula like Raymond asks, or if not derive, it should be given to you, hopefully, for the question. And then after differentiating, you simplify as much as possible. The rest will be remembering the various differentiation techniques we learned. Remember last semester, differentiation, we have the product rule when you're multiplying two terms. We have the quotient rule. Sometimes you have to integrate by parts and things like that. But apart from those techniques, the rest, if they are trig inverse function, you only have to remember the standard. I think we should try one more. Oh, this one too has been done. Okay, so this involves 2 e raised to the power x. Okay, I want something. So, okay, I think okay, this one hasn't been done. Let's go through this. Now, sine we know is 1 over 1 minus u squared. Okay, so again, my u is 2ex. So first of all, there is a constant half here. So the half is outside. And then we have 1 over 1 minus u squared gives me 1 into bracket 2ex squared. Now, this 2 here will cancel the 2 outside here. So the numerator now becomes e raised to the power x. When I expand the denominator, I'll get 1, then 2 times 2 will give me 4, and e becomes e raised to the power 2x. Then all I need to do is multiply the numerator and denominator by this, and then we get same as this. So all these examples are supposed to help us differentiate this trig function. This one hasn't been done, so let's try this before we look at the implicit function. So here, I'm dealing with sec, and I'm dealing with cosec, okay? And we are adding these two functions. So what I need to know is what is the standard differential of sec inverse, and what is the standard integral of cosec inverse. So I have quoted them here. Sec inverse is 1 divided by u into and root u times square root of u squared minus 1. And then the cosecant is the negative in front of that same function. So let's see if we can weather the storm with this one. I started doing it so that we can follow the steps. So here, the numerator is 1. So this is supposed to be 1 here. And then the denominator is supposed to be u, then the u squared. Now my u in this is 5t. So 5t is outside, that is u. And then the u squared will give me, I hope you can see that it gives me 25t all squared. Okay, I'm jumping some steps so that we can see our answer very soon. So 5t all squared will give me 25t squared. That will give me the u squared. All this minus 1. Okay, now whatever I have here, I'm going to need it as I go on. So let me copy it. Now then, if I differentiate 5t with respect to t, I'm going to get 5 because the power there is 1. Now let's go to the cosecant one. The same thing is going to happen. This time, this is supposed to be minus 1, okay? So that gives you minus 1. And then if I differentiate 5t, I'm going to get 5. And then here, I'm going to get the same function that I have. So that gives me 25 squared minus 1. Now, please take your time and look at what we have here. The numerator here becomes 5. And the denominator here becomes 5t. Then the square root sign comes in. Then on the right-hand side, please watch, this is plus and that is minus. So actually this is supposed to be minus the same thing that we have here. That will be 5 divided by whatever I have in the denominator, 5t, and the square root of the function that I'm dealing with. Now, so if it's this minus this, then my answer simply is going to be 0. Okay, so my function of t, they will cancel out because the sec inverse of a function of the same angle and cos inverse of the same angle is giving me 0. Okay, so that will take care of this example. There's one more example. When is my implicit? I have so many examples. Okay, so let's maybe do one more, and then the rest, I will leave them for you to try. I think it's up to 9, and then there are some questions here. So let's try, I think number 7, cot inverse, and then the rest, I hope you can do them yourself or follow through what I'm doing. So let's look at number 7. We want to find cot inverse of 2 over x. I hope you know that this can be written as cot inverse of 2, and then your x will be raised to the power minus 1. I don't know whether you can see that, but whatever it is, we need to quote the cot inverse function. Now, to find the cot inverse of a function, it is -1 divided by 1 plus u squared. There's no square root in this. So you see, I have even created this. This will be x raised to the power minus 1. Okay. So let's substitute our angle, this is our angle, into the formula. So first of all, the numerator is supposed to be -1. So this is -1. And then the denominator is supposed to be 1 plus, again, this one is supposed to be 1 plus. So 1 plus. Okay, so if you differentiate, if you take this and then you square it, what will it give you? 2x raised to the power minus 1 all squared. What would that give you? Two squared is going to give me 4, isn't it? Now, x raised to the power minus 1 all squared will give me -2. So that gives me x raised to the power -2. So that is why x goes to the denominator. So it gives me x to the power 2 squared. Now, this is 1 plus u squared. So all this squared here at the top here. I hope you follow. 2x to the power minus 1. When you square it, it gives you 4x to the power minus 2. The -2 makes sure that x goes to the denominator. 4 goes to the numerator, and then we square all that. Now then, when we differentiate this, what do we get? When we differentiate this, we are going to get -2. All right. I'm going to get -2, and then this gives me x to the power -1 minus 1 will give you -2. So that gives you to the power 2. Okay. So how do we simplify this? The numerator, -1 times -2 should give me +4. The denominator, I'm supposed to get, I think, x squared. That is for this term here, x squared. And then this term, which is left here, the denominator, into brackets, I'm going to get 1 plus, that will be 8. 8 divided by x to the power 4. 4 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 to the power think you should get something like this. Okay. And I don't think you can simplify this. Well, you can simplify this by multiplying through the numerator and denominator by x squared. So this will give you 4 divided by, the denominator will be x to the power 2. If you expand that, x to the power 2. And then on the right-hand side, we are going to get 8 divided by now you remember this x squared here will multiply 8 over x4. So it will cancel the x4 too. You will be left with x to the power 2. I don't think we can simplify this any further. Okay, so this should give us a solution to our problem. Okay, the rest, you follow the various trig differentiation formulas. This one, you have to use product rule. Keep one constant, keep x squared constant, differentiate that, and then come and keep this one constant and differentiate that. Okay, so I think I've done that. So you see that here, remember this became 1 plus u squared. So I keep x squared constant, and then I differentiate tan inverse. So tan inverse, I have to use a formula here. So that gave me 1 over 1 plus 3x squared. Then I differentiate 3x, it gives me 3. Now, then I keep tan inverse constant and differentiate x squared. That gives me 2x. Now, when I simplify what I have here, I'm going to get x squared outside. Now, 3 will multiply the 1, gives me the 3 in the numerator. Then I expand 1 plus 3x all squared. It gives me 1 plus 9x squared. The right-hand side will give me 2x, then tan inverse of 3x. Now, to simplify this, all I try to do is I try to put all this into one bracket. It means I find LCM. Okay, so this one, the whole of this will have LCM of 1. Denominator is 1. And then placing them so that x multiply. You see that there's a 2x here and there's an x squared here. So if I'm able to take one of the x out, I'll be left with x here, and then one of the x goes into the numerator here. So the numerator gives me 3x plus 2, using LCM, 1 plus 9x squared, then tan inverse of that, all divided by this. So please, what I did from here up to here is I found LCM of this, basically. Okay. Somebody will ask, can I leave it like that? Okay, so remember the questions, all of them is telling you that when you are given the problem, simplify, simplify. So that is why we went ahead to show this. Okay, so we've seen sine inverse, we've seen sine inverse, we've seen cos inverse, we've seen cot inverse, we've seen tan inverse, we've seen cosecant, and we've seen sec. All the trig functions, we have seen examples of them. Okay. The last example here is on cosecant. We can look at it and also do. Then I've given some 10 questions here. This one basically is straight away chain rule. This one, you use product rule because this cos inverse of sine. And this one, you use chain rule of the trig function. This one is straightforward. Please remember that our cosecant, I mean, it's a cos inverse, cosecant inverse. That's why I use the product rule. Okay, so these are some questions you can try your hands on for you to be able to be familiar with the technique. Okay, so that's the first part of our problem. There are more questions here. The second part is a little bit straightforward, but also it follows the rules of what we call implicit differentiation. We are going to explain the concept of implicit differentiation. First of all, when you are given a function that involves x and y, then what we mean by implicit form is that you have y and x together. When we say explicit form, then it means that y rather is in terms of x. So y is the subject. We want to make sure we understand the terms or the concept here. Implicit means that the x and y are together. Okay, implicit, they are together. And then explicit means that one of them depends on the other. And then what we are supposed to do is how do we differentiate whether the function is an implicit form or an explicit form. All this while, what we've been taught is explicit differentiation. Y is equal to this, f of x is equal to that, g of x is equal to that, h of x is equal to that. But what if this time I say x squared plus y squared is equal to something? That means the equation x and y are together. So how do we differentiate? How do we go about it? So I'm going to take an example where I'll give an equation and then I will show you how to follow the explicit format, then how to follow the implicit format, and finally see that the results will give you the same thing. Okay, so this is that second part of our outline for today. So if you are going to differentiate with respect to x, now, first of all, we must understand the properties. What do we mean by the properties agree? So let's say that I want to derive when the denominator disagrees. So when the denominator agrees, you use the properties of differentiation. What do we mean by properties? You can use chain rule, you can use product rule, you can use quotient rule. That is the properties of differentiation. But when the denominator disagrees, then we use the chain rule and the properties. I'm going to explain all this. For example, if you take 4x squared, we are differentiating respect to x. You see that the denominator x, it corresponds to the function, okay? So here the denominator agrees. So we basically use the chain rule. 4 times 2 gives me 8x. Now, the second example, my denominator, which is dx, does not conform with the function itself. This is in terms of y. This is 3y squared. Then here we are going to use, when they disagree, we use the chain rule. Chain rule is that you differentiate with respect to the function and then differentiate the function itself with respect to x. I hope you understand. Differentiate with respect to the function and then differentiate the function with respect to x. Okay, so 3y squared will become, when you differentiate 3y squared, you get 6y. Now come and differentiate y, because y is not x. You now differentiate y, it becomes dy dx. Because this function, the denominator we are differentiating with respect to is not the variable in which the function is in. That is all we are going to try to do in implicit differentiation. When the denominator disagrees with the function, then we use the chain rule. The chain rule is differentiate the function with respect to the power, and then come and differentiate the function with respect to the denominator, dy dx. Any question on this? Okay. Okay, so these are the guidelines we want to follow. Dy dx, we want to differentiate with respect to x. So differentiate both sides of the equation with respect to x, okay, using implicit differentiation. So whatever the function is, because x and y are together, the left-hand side of your relationship differentiate with respect to x. The right-hand side, you do the same thing. Now, then you collect like terms involving dy dx. On the left-hand side, left. Yesterday, I was really tired, left side of the equation, and move all other terms to the right-hand side. Then factor dy dx out of the left-hand side of the equation and then solve. So implicit, differentiate left-hand side and right-hand side, then group all like terms together, then factor out dy dx and then solve for that. Okay, so let's take an example. On the left-hand side, my function is the same equation I'm dealing with. Please just realize that I'm dealing with the same equation, okay? On the right-hand side is the same equation, but this time around, I'm going to use deriving the equation implicitly. So watch. For me to be able to do explicitly, it means that y must be in terms of x. So I make y the subject. If I make y the subject, then it becomes y will be equal to 5 minus x squared. Because it's a square, it's a square sign, it becomes plus or minus that. Let's do the left-hand side first. Now, dy dx simply will give you, remember this is 5 minus x squared raised to the power half, okay? That is why it becomes 1/2, 1/2 of the function. Then you differentiate the function itself. If you differentiate 5 minus x squared, you will get negative 2x. That gives me what I have here. So the numerator will give you minus 2x in the numerator. One of the x will cancel the x that I have. Sorry, 2 will cancel the 2 in the denominator. So the numerator becomes negative x. And the denominator becomes square root of 5 minus x squared. But you already know that the value y is giving us plus or minus 5 minus x squared. So this thing that I have here, the denominator here, will give you the value y. So the answer to the differential of dy dx becomes negative x over y. Now, for explicitly, remember the rules that I listed here. Remember, differentiate left-hand side and right-hand side, and then group like terms. So that's what we are going to do. So my left-hand side is this part of the equation. My right-hand side is this part of the equation. Now, left-hand side, this is dy dx. We are differentiating with respect to x. So that will give you 2x. Now, this function is not in terms of x. So that will give you differentiate with respect to the power. That gives you 2y. And then differentiate y with respect to x. That gives you dy dx. Now, remember what we are supposed to do. Bring all the dy dx to the left-hand side and take all the terms without dy dx to the right. So 2x will go to the right-hand side. That gives me negative 2x. And then I have 2y times dy dx. Now, make dy dx a subject. First of all, the 2 here will cancel the negative 2 there. Then I have dy dx on the left, and then I have negative x on the right. If I make dy dx a subject, that means divide through by y, I'll end up getting the same answer that I got here. Okay, so we are explaining how implicit differentiation differs from explicit differentiation. But if you do it correctly, we should all come out with the same answer at the end of the day. Okay, so the rest is trying and doing some examples. I think example 1 I've done it. Example 2 we haven't. So let's see example 1. 3xy to the power 4. If I differentiate this with respect to implicit differentiation, first of all, I hope you realize that this is a term that you have to use product rule, because you have a constant, we have x variable, then you have y variable. So I am going to keep the one of the terms constant and then differentiate the other. Now here, because 3 is constant, I pulled that out, and then I kept y to the power 4 constant, and I differentiate x. If you differentiate x, you get 1. That's why this gives you 3y to the power 4. Now, I'm going to now keep x constant. If I keep x constant, if I keep 3x constant and differentiate y, I'm going to get 4y cubed. I hope you see it, 4y cubed. And then I differentiate y itself with respect to x. That gives me dy dx. Remember, I'm keeping 3x constant. I could have written that at the beginning here. So 3x is kept constant. I differentiate y, I get 4y cubed, and then dy dx. Now, what do? We now try to bring all the terms in terms of dy dx to one side. So remember that there's a dy dx on the left-hand side. That is what we are solving, dy dx on the left-hand side. And I have another dy dx on the right-hand side. So I am going to bring all these terms to the left. When I do that, I get dy dx minus 4y cubed dy dx times 3x. Then the only term that is left on the right-hand side becomes 3y to the power 4. Now, if I factor dy dx out, I'm going to get 1 minus 4y cubed times 3x, all equal to the 3y to the power 4. Okay, then I multiply 4 times 3 gives me 12. And therefore, the term in the bracket becomes 1 minus 12xy cubed. If I divide both sides by the term in the bracket, then I will have 3y to the power 4 divided by 1 minus 12y to the power 3. Okay, so this is an example on implicit differentiation. Let's try this question. I'm not too sure of what I have on the right. I'm supposed to show that the answer is supposed to be this. I think I did this so that if I'm getting it wrong, we can all follow through. I don't see 38 in this. The material I picked this from did not give me the equation clearly. If this doesn't work out, maybe I'll look for another example. Maybe let's do this one. Okay, because I don't know. I think it's not supposed to be 38, but if I differentiate and I'm not getting that, it's just going to be something with. So I'll verify this later. Let's take this rather and do this. It says determine the slope. Please, slope, remains find the differential of this. So we are going to differentiate with respect to each of the terms and then group like terms. Now it's because I want the equation to show. So let's take, if you differentiate 3x, x cubed, you're going to get 3. You're going to get 3x to the power 2. Okay. And then who can help me out with this? When I differentiate the y cube, what should this give me?
So, sir,
Yes.
it becomes 3y squared
3y squared
dy dx.
dy dx. Okay, so that gives me the y dx. Sorry, that's not what I want. Okay, now on the right hand side, remember they are together. So you must keep one constant and differentiate the other. So if I keep a 2y constant, differentiate x, I'm going to get 1. Then I think plus, you now keep 2y constant. Sorry, I kept 2y constant. Now I'm going to get 2x constant and differentiate with respect to y. I'm going to get y. If you differentiate y, you get 1. So you end up getting the y dx. Okay, so that is what we are supposed to have here. Now then, what do we do next? We group like terms. So I have dy dx here, and I have dy dx here. So I'm going to bring this 3x to the right-hand side. Okay, so I'll be left with 3y squared. Okay, and then dy dx on the left. Then I bring the term on the right. So when for its plus here, it comes to the left, that gives you minus I'm going to get 2x why has this thing changed? Okay, 2x and then dy dx. Okay, then on the right-hand side, I'll be left with 2y, and then I take 3x squared there minus 3x raised to the power 2. Okay, now if I factor dy dx out, dx out on the left-hand side, supposed to get 3y squared followed by minus 2x. Okay. Minus 2x. Okay, then on the right-hand side, I'm going to have 2y squared, 2y minus 3x squared. Okay, so if I divide both sides by this, so the numerator here is going to be this term here, and the denominator here is going to be that term here. Okay, Now, then it says that, remember the question said that find the differential of this and this at the point 1, 1. So we are going to substitute the value 1 for y, the value 1 for x. Then we evaluate this. Just want us to see everything so that. Okay, so where are we? We are here. So if I substitute 1 here in the numerator, x is y is 1, it gives me 2, 2 times 1, and minus 3 times 1 squared. And the denominator will give me 3 times 1 squared. And down there becomes 2 times 1. Okay, so finally, the numerator will become, this will be 2 minus 3. That will give you negative 1. And then the denominator will give you 3 minus 2. That will give you 1. So my answer here should be equal to negative 1. Okay, so that will be the solution to the question we have at the top here. Okay, so we were given this, and then we were asked to be able to determine the slope of that, and we have done that, and it's giving me that. Yeah. So that is one application to implicit function. You differentiate with respect to x. When you are done, then you substitute in there. Okay, so I just took one example. I was trying to finish this slides yesterday, so I wanted to have examples on it. So the rest will come in the worksheets. Okay. Now, so the last part of this morning's lecture is applications. Please, differentiation has lots and lots of application in almost every engineering topic, biology, even though engineering, come to medicine, comes to, I mean, a whole lot. Mathematics itself, finding the maxima and minima situation. Hopefully, Unit 2 will take care of some of these things. But at the end of the slide, I have some few examples I've shown. I didn't have time to type all of them, so some of them are screenshots. So please bear with me. Now, so one of the properties of application to differentiation is how to determine whether a function is increasing and decreasing, okay? So determine the set values x in which a function increases and where it decreases. So I have this graph, it's a screenshot, given the turning point at negative 460 and the other turning point at 2,60. So where is it decreasing? So x is decreasing from -4, from here, from -4 all the way up to, and between -1, x -1, all the way up to 2, positive 2. So this, the arrow coming down is a decreasing function. So from here, all the way up to this, x less than -4. So from -4 all the way to infinity, x is decreasing. And then from the value 1 all the way up to the value 2 is decreasing. And where is increasing is the arrow going up. Okay, so this graph, it's telling us that, and how did they get this point? The reason why this is an application is that how to get the point -4 and 60 is actually differentiating this equation and substituting and equating it to 0. And then you are able to find the minimum turning point to know where they are turning and the maximum turning point. So it's an application to differentiation. You have to differentiate to get the turning point and determine where the function turns and where it increases and where it decreases. That's one. Then sometimes you'll be asked to find the stationary point. The stationary point is actually also the turning point. So find the point on the curve when its tangent line has a gradient of 0. That will be the turning point. So if you are given an equation x squared plus 4x minus 5, you differentiate and equate to 0, you end up getting x equal to -2, substitute x equal to -2 into the original equation. -2 squared will give you 4. 4 times -2 will give you -8. -8, then 4, and then -5 will give you -9. So that's how they were able to get the value -2 -9. So the nature of stationary point determines or tells us the behavior of that stationary point. So stationary point is a point where it's a tangent line and it's either horizontal or vertical. Now, how is it related to differentiation? Now, this same equation we differentiated, remember when we differentiated the first function, we got 2x plus 4. If you differentiate this function again, 2x plus 4, you get 2. Now, this 2 means that the -2 minus 9 is the minimum point and the value of the second differential is greater than 0. So when they ask you to find the nature of a turning point, all you are supposed to do is differentiate twice. Okay? When you differentiate twice, it tells you that the second differential should either be a positive or a negative value. So it is turning at -2, -9, but the nature of it is that turning point is a positive turning point. It means that it is greater than 0 because you got 2. Okay, I think there's another example here. Yes, this one. So this is -2 +9. Again, when you differentiate the equation, the first one, we got the value to be -2x -4. So we know the turning point as -2, 9. Now, if you differentiate -2x -4, again, you get -2. So here, the maximum turning point was less than 0, and the minimum turning point was greater than 0. So that is how we determine the nature of a turning point. Okay, so the first differentiation tells us the turning point. The second differential tells us the nature of the turning point, whether it's positive, that is greater than 0, or whether it's negative. Okay, there is another example here. This one, it's supposed to be a horizontal line, 0 and 3. Again, if you differentiate twice, you are supposed to get, the first one, we got 3x squared. The second one, we got 6x. Now, what is the nature of this point? So what you do is that you are going to substitute x equal to 0 because the point where it turns was 0, 3. So what happens when x is approaching 0? And when x approaches 0, the function goes to 0. So this point is neither a maxima or a minima. It is not a maximum turning point or a minimum turning point. It is called a stationary point or a point of inflection. Okay? Now, a point of inflection is a point where the value approaches 0. Okay, so we've seen an example where we have the second turning point, the second differential gives us a negative value. Okay, that is a maximum point. And then the second differential gives a positive value, that gives us a minimum point. And then we've seen a second differential that gives us a value to be equal to 0. And that one, we call it a point of inflection. It's an inflection, okay? So, how do we apply this concept? So first of all, you find the coordinates of the stationary point on the curve and determine the nature of this point. Then secondly, you sketch the graph and determine whether the value of x in which the function increases and decreases. So number one, what are the strategies to solve this equation? Differentiate the function and equate to 0. Number two, find the second differential and identify the nature of the point. Then point 3, plot the stationary point and sketch the graph. So in determining the behavior of equations or the nature of their turning points, you go through these 3 steps itemized here to be able to identify that. Okay, and so that this question that I've been given here, x cubed minus 3x plus 2, that is the solution here. First differential, we got a value. Then we do second differential, we got a value approaching -6 maximum point, and then +6. And therefore, you are able to explain the behavior of the graph. Okay, so now I have, I think, 1 or 2 questions that are very applied. So an open tank with a square base is to be made from a thin sheet of metal. Find the length. Hey, yesterday there, I was like, length of the square base and the height of the tank so that the least amount of metal is used to make the capacity. Now, how do we go about a problem like this? So you see an application is differentiation all right, but it's a story problem. Now, what are the strategies to solve this problem or this question? First of all, derive the function from the surface area or the volume. Then express the function in one single term, and then use the function to identify the maximum or the minimum point. Okay, so application questions like this, we must remember some few things that we learned in either physics or in chemistry to help us to do that. So what did they do? First of all, we know that to find the base of the sheet, find the length of the base of the sheet and the height, so that at least the amount of metal used to make the tank with the capacity of this. We must remember the volume formula. We must remember the surface area formula. Okay. So for questions like this, if you should come across this, either we may provide you with the original formulas for the equation, the volume, and then the surface area. And then based on that, you can be able to derive the equation. Without that, it will be very difficult to be able to solve these problems. Okay, but my aim for bringing these examples here is to make you see that differentiation has a lot of applications, so many of them. And one of them is what you see here. Okay, so we may need to recap some few formulas to help us solve the problem. We're able to do that. Then the mathematics we are learning is just applying the differentiation with respect to the problem you have. Okay, so I ended by showing you that when you see the equation or the formula dy dx, it means the change with respect to y for every value of x. Okay, so when you have the radius of a circle, and then you are supposed, and they give you a value like the 0.2 centimeter per cms, that means that this is the differential of the radius with respect to the function. When it is water, then you have to volume respect to the liters. When it is metal, then we have doing surface area respect to t. So when you have when you have values like this, something slash something, something slash something that we come across, they are actually differentials. Okay, what do we have? Speed is equal to distance times time. So if you make time the subject, or you make distance the subject, then you see that you end up getting something divided by something. We are saying that those types of equations are basically applications to rate of change, and we can use those differentials like that. So there are some examples that I have here. I screenshot some of these. Some of them are not too clear, but I retype them to explain what they are all about. Okay, so basically, that is what I have for you today. It's a lot, but I hope when you take your time and go through the examples, you definitely will be able to follow through, at least the first two. As for the application, depending on area, you're electrical engineering. So we may even have areas with respect to your field as well. I've brought something with respect to chemistry, respect to biology and physics as well. But there's definitely examples that may apply to you. Rate of change of heat. These days when you are building a house and you are supposed to do the wiring used to be outside. Now the wiring of buildings are inside, and you're using PVC. And you just realize the type of weather changes and temperature changes. So you may have to decide what type of PVC or what type of cables you use, because there will be differentials in there, a little bit of temperature. And concrete, for example, if you are laying wires in concrete, there are certain standards of pipes that are supposed to be used. But over time, some of these pipes can crack depending on what method. So all these things comes to play in terms of our area of expertise and what we are doing. Okay, so any questions from what we've seen this morning? If not, then I'll show you the worksheets. The worksheets are step-by-step questions to help you follow today. So any questions or any comments? Okay. Okay, so on the elements, like I said, I have placed a lot of worksheets. Please, these worksheets, like I said, they are practice questions or they are practice materials to be able to explain the topic. And for most of them that I gave, the answers are within. So you can be able to solve and be able to check your answers. So I have 2 worksheets on inverse trig functions, A and B, 6A and 6B. Then I have 2 on implicit. Then I have actually 3 materials. The 3 materials, there's only one that is a question. The rest are reading materials to explain. I think I'll start from the last first so that you can appreciate what we've done today. So the last material is on application of differentiation. I pulled these materials from some of the online websites. So it started from the basic differentiation that we've done. So how to plot graphs, how to sketch them, maxima and minima. Hopefully next week I'll look at some examples, and then basically how to apply them. So it starts from simple functions to polynomials to limits, okay? And then finally, the differentials of the function, the exponential function. So if you take your time and go through this, you will see that some of the things I've talked about at the end, whether a function is increasing or decreasing, whether a function is a stationary point, what do we do? First differential, is it second differentials? They are all in here to explain some of the things that I referred to you about. Okay, and they are explaining the behavior of the curve, whether it's increasing or it's decreasing at the point of differentials or stationary point. Okay, then at the end, there are exercises. Some of them has been done. You saw the equation we solved. So find the behavior of a stationary point and determine its nature. Okay, so that's an application to this. So you must do first differential and do second differentials. And depending on the values, you can be able to explain. Okay, so this material will help you to understand what I was showing you in the PowerPoint. Okay, then I just want to see how far it went. So most of them are curves. Then at the end, it will give you some applications, not just mathematics differentiation, but basically things that needs to be done with respect to engineering. Okay, so it's a good material to use to be able to understand the concept of applications of differentiation. Now, then let's start with the trig inverse function. So please, this particular tutorial or worksheet, the answers are at the bottom. So if you take your time and find the inverse of the trig function using the standards that I've given you, the answers are at the bottom. Like I said, they are here. But like I told you last week, don't just look at them. So use the standards that I've given you, differentiate them, and then go back and look at whether you're getting the answers correct. So this is for the inverse trig function, and then this is the second one. This one, there are no answers, but you go through the same standard. So it starts from the normal linear, oh, this is implicit, oh, this is trig inverse. So we start from the normal log and exponential functions we did a week or 2 ago before we start looking at the inverse of the functions. Okay, so that's the second one. And then the third one is the one on implicit. So here you've been given a function in terms of x and y. So remember the rules. First of all, you differentiate left-hand side and right-hand side, and then you group like terms, and then you solve or simplify. Okay, so this one too, I think the answers, do I have answers? Yes, the answers are at the bottom. Okay, so try them, try your hands on these examples, and make sure hopefully by next week you should be able to handle all this. This is one question on application. So this one is application, okay? So the questions have been given, and then you are supposed to, the initial one, they are just simple differentiation. And then we start looking at some questions on how to apply them. We'll find the equation of the normal line to this curve. So that's an application. Find the coordinates of P with the curve this, which is normal to that. That's also an application. Find the radius, okay? of a hemisphere, and they're giving you this. So you must actually be able to have a relationship involving the radius of the equation, and on and on and on and on. So all the things we've done today, we have questions here to help you to be able to understand or go through them. I know that we pile you a lot with a lot of materials because we don't meet often physically. So the idea is to be able to have something to do when we are not meeting you physically. We only meet once over the weekend. So kindly take advantage of those materials that we are giving you and do what you can. The idea is not to overwhelm yourself with the one like we did last semester. The ones you are not able to do during our physical meetings, we should be able to sort you out. I'll make the solution of all these, these are solutions of all these materials available, or hopefully before you even take any major exams. And lastly, like you say, you know that normally I like to give tutorials or MCQs on the various topics. Okay, but unfortunately, I haven't been able to create my question bank, so I've not been able to activate any of them. But I hope by the time we are through with maybe the first 3 units, I should have some questions that will help you to handle MCQs from there, because your midterm will definitely be online and it will come from those question bank. So that one is on me. I have to work hard on this, and I'll try my best to be able to get the questions as soon as possible. Okay, so I'm done. Any questions, any comments, any recommendation? Did I haven't heard Philip's voice? Philip, how are you?
I'm fine, sir. I'm fine, sir.
Okay,
Thank you.
you're welcome. Okay. Okay, so if you don't have any more comments, any questions, then we'll wrap up here. Please kindly take care of yourself. We're having so many bad news from our students. So those of you who are not in Accra, maybe you may not be experiencing those things, but there's a lot of things going on. We need, what's the word? We need, our minds should be in safe bodies to be able to work well. So whatever you're involved in, please make sure you are safe. Don't take unnecessary risk. And I know we need to work and put food on the table at the same time to take care of ourselves, but please do them within the confines of what you are capable of. I pray that we also through this period in which we are in, so that we can also succeed in our individual endeavors. Okay, so enjoy the rest of the weekend. Wish you all the best. God willing, next week we'll continue with where we left off with Unit 2. Yeah. God bless you and take care.
Okay, sir. Bless you too.
Okay, bye.